Now we're going to see how we can get from that general equation of the merge sort algorithm to a big O or a theta notation. So it's really as simple as it can be. So let's go ahead and rewrite what we had last time. And I'm dedicating an entire video to this because people fucking hate logs. Let's be honest, right? Logs are a thing that you never understood how they work. They look like magic. You tried to just sneak by math class without ever really learning them, and they still scare you. Doesn't matter how old you are, logs are still the most terrifying thing in the world. We will need them a lot. So let's use this video to move slowly through this. So here we have t of n is equal to 2 to the k times t of n over 2 to the k plus kcn. If you don't know how we got there, check the last video and the few ones before that. It's a full, mini series on the merge sort algorithm. So now we want to essentially say that n is equal to 2 to the k. And what happens if we say that n is equal to 2 to the k? Well, that would mean that n over 2 to the k would have to be the same thing as 2 to the k over 2 to the k, which would have to be the same thing as 1, which would mean that n over 2 to the k is going to be n1, which is going to be a constant. And that will essentially be staying out of our way, and you'll see how that will be done in just a moment. Now, the problem is we want to do something about the other values here, which is the k up here and the k over here. We've already solved this over here, and we were able to solve this pretty easily. But how do we solve these other values over here? It seems like we could handle this whole 2 to the k thing easily by just replacing that with n. But then how do we handle that k with the kcn on the other side, right? So we're going to need a log to do that. Logs are scary, so let's work through this really, really slowly. So for the people who don't understand logs at all, we are going to see them right now. So let's get some colors going here. We know we have n is equal to 2 to the k. Now, for logs, the formula for it, I guess if you will, the recipe is going to be log. Down here, you're going to write the base, which is essentially what number is getting affected by the exponent. Up here, we see that it's going to be 2 as the base. Then we have the result here. Essentially, it's going to be what's on the other side of the equal sign. And then we're going to have the exponent. So we can see up here, it's easily to just translate what we had up here into log form. What is the exponent? Well, the exponent is clearly k. We have our equal sign, so we'll go ahead and write that down there. Now we'll have the log. What is the base? Well, the base is what's getting affected by the exponent. That's going to be 2. And then the result here is going to be this. So the base over there, and then the result is going to be n. So we can write that a bit more compact. The log form of what we had is going to be log 2 to the n is equal to k. So we can essentially go and replace all of the k's that we see with log 2 to the n. Simple as that. So let's go ahead and do this here. It's going to go ahead and we'll go back from the start again. Well, we'll use the one that we had, the more simplified one, I guess, which was 2 to the k. We already had that this is going to be t to the 1 plus k c. And I'm moving through it slowly, right? Normally you should all do this in one step, but I'm going through it slowly just so we understand. So let's go ahead and replace these k values with log 2 to the n. So up here, we will have 2 log 2 to the n times t1, which is going to be a constant, which we'll replace with something like this, like a c we have over here. I'll use a different c because it might not be the same one. So we'll want to make sure we split those up. And then we'll have log 2 to the n times c times n. Now we're looking at this over here. What is going to be 2 to the power of log base 2n? Well, if we work through it, it's going to come out to n, right? Because we can say technically, let's scroll down here. We know that log 2 to the n is equal to whatever the exponent is going to be. And the exponent for this is going to be k. And then we would have 2 to the k. So if we want to make a little bit of a pattern here, this would essentially go back to being 2 to the k, which we know would be n. You know, it might seem redundant that we went all the way over here when we clearly could have replaced 2 to the k with n, but this is the proper way of doing it. I am going a bit slower, but this is the way you should be showing it. It might seem redundant, I guess it is, but it's the best way to show it, and it will make more sense with some other algorithms that we're going to be seeing. So we can start writing this back out over here. I want a nice color. This, you know, as we're approaching the end over here, we'll go to, I don't know what this is, magenta, whatever. N, so this is going to be n, multiplied by t to the 1 here, where this is going to be a constant. So I'll go ahead and I'll call this c prime, right? So it's going to be a bit different than this c. So it's essentially the same idea, but we don't know if they're the same right now. So we'll just go ahead and call them separate, but they're going to serve the same function. It's just going to be some constant. Now, what is this here? Log base 2 to the n. Well, that's essentially, when you just keep it general, it's just going to be log n. So we can say plus log n multiplied by c multiplied by the n. This n never went anywhere. So that's what we're going to wind up with. Now, when we're talking about big O and big theta, or at least theta, which is the one we're going to use here, it's a tighter bound because it says it's not greater, or it's greater and less than at the same time, or less than or equal to, so it's going to be the exact same thing. It's a tighter bound. You have both sides coming at you. We want to know which one's really going to be calling the shots. Who is calling the rate of change shots over here? You know, based on your input size to the runtime, who is really making the decisions? We have n multiplied by some constant, which means essentially the one that's driving this part of the equation. Let's get another color here. Essentially, this part of the equation is being driven by n, and this part of the equation over here is being driven by n log n. So which one of these is going to be bigger? Now, when you're thinking about the values of log n, the best way to think about it is it's going to be just a bit smaller than n. So think of it as a weaker n. So what's going to be bigger? N, or n multiplied by a value that's going to be a little bit smaller than n? Well, n log n is going to be bigger. It's going to have a bigger impact on the rate of change. So essentially, we are going to, for the sake of the big O, this is not going to be considered. It's going to be n log n, which means that one is going to win the contest, and that one will be, we're actually going to call this theta because it's going to be a tighter bound. The theta will be n log n. And that's how we get that runtime. The essential final answer for the MergeSort algorithm is going to be theta of n log n. That's going to be essentially what's dictating the rate of change. It is the more dominant of the two factors that we see in here. So I hope you guys enjoyed. If you have any questions, leave them below. This is insanely confusing when you're starting off. This is not the first algorithm you'll see when you actually work through it in detail, and it is confusing. So if you have questions, leave them below. I'll probably eventually, towards the end of the series, make full videos on each algorithm, right? So you don't have to go ahead and find like the 4-part mini series for each one. I'll make a full video, which is going to be everything you need to know about each algorithm. So look for those as well. I hope you guys enjoyed, and I'll see you in the next video.